Well, hello and welcome to the first lecture. In this first installment, we're going to revisit the basics of functions. Many of you are probably familiar with functions from previous algebra courses. Nevertheless, it's going to be good for us to start with a little review and set the stage for the rest of our investigations this quarter. It's no secret that functions are very important both in pure mathematics and also applied mathematics. In fact, they're hiding everywhere, even everyday life. So let's start with a pretty simple but relatable example. Most people have worked a job that pays by the hour. So let's start by supposing that someone gets paid $15 an hour. And consider the following table of values. Here we use H for hours, and P will stand for payment or an amount of money. Note that for each hour worked, there is a corresponding amount of money that you have earned. We say that your pay depends on or is a function of the amount of hours you work. We can even write down an equation that captures the relationship between hours worked and pay, namely P equals 15 times H. This example illustrates the following definition of a function. A function is a rule that assigns to each element of a set A exactly one element from another set B. In our example, set A is a set of values representing possible hours one can work, while set B is a set of corresponding monetary values. The rule is simply multiply the number of hours worked by 15. It's important to note that the term rule is quite general, and we need not be able to write an equation for it. All that matters is that each element of A is paired with exactly one element from B. In fact, arrow diagrams can give us a visual of this. Let's represent set A by a blob and suppose its elements are 1, 2, 3, and 4. Represent B by another blob and suppose it has elements 8, 9, and 10. One possible rule would be to assign 1 to 8, 2 to 8, 3 to 9, and 4 to 10. Now the fact that both 1 and 2 get paired with 8 does not disqualify this from being a function, since it is still true that each element in A is paired to only one element of B. In other words, 1 only gets paired with 8 and nothing else, and likewise 2 only gets paired with 8 and nothing else. For short, let's label this rule or assignment F. We can think about F as a set in its own right, namely a set of ordered pairs. More specifically, this set of ordered pairs. Let's contrast this with another example. This time, let A be the set containing just 1 and 2, and let set B stay the same. Now consider this arrow diagram. In this case, we see that 2 is paired with more than one element from B, namely both 9 and 10. This is illegal and so is not a function. Now let's turn to some important terminology and notation you will see over and over and over again. A common analogy for a function is a machine, where something goes in, the machine does something to it, and the result comes out. In light of this, we refer to the elements of the first set, or the things going into the function, as inputs. The results, which belong to the second set, are called outputs. Though not necessary, it is convention to represent inputs by the variable x, which is also known as the independent variable, while y is typically used to represent the outputs, and that is referred to as the dependent variable, since of course it depends on what x is. The rule, or the function itself, is represented by some other letter like f, usually, and we write f of x equals y. This equation can be thought of as saying f acts on the input x to produce the output y. So x gets turned into f of x. In other words, f of x is another representation of the output. We can also think of it as representing what happens to x. So if the rule is square the input and add 5, then the equation f of x equals x squared plus 5 just means that x turns into or is transformed into whatever the quantity x squared plus 5 is. Now for some more terminology. The set of all inputs for a function is referred to as the function's domain. The set of all corresponding outputs is called the range. We'll denote these by DOM of f and RNG of f, respectively. We can now define a function a little more rigorously. It consists of essentially three things: a domain, a range, and a rule that assigns to each input of the domain exactly one output from the range. This update helps to illustrate or highlight the fact that different functions can actually have the same rule. For example, consider the rule f of x equals x squared, but where the domain is 0, 1, 2, 3, and again f of x equals x squared, but with domain -3, -2, -1, and 0. These are actually different functions even though the rule for each is square the input. They're different because they have different domains. Different rules can be applied to many different domains. However, certain rules can have inherent limitations regarding allowable inputs, which naturally restricts their possible domains. An input is allowable if the rule assigns it to or produces a defined output, or in our case, a real number. To illustrate this, consider the rule f of x equals 1 over x. This represents a real number for any x value that isn't 0. In other words, the rule is not defined for x equals 0, and so 0 can never be in the domain of any function using this rule. Very often, when we talk about functions, we will simply write down the equation defining the rule for producing outputs, and take the domain to be implied as the largest set for which the rule is defined. For instance, if one simply writes f of x equals 1 over x, then the implied domain is the set of all real numbers such that x is not 0, or from -infinity to 0, union 0 to infinity, not including 0, of course. This is because 0 is the only real number for which 1 over x is undefined. If we wish to talk about another function using the same rule, 1 over x, then we must explicitly state the domain. Let's look at another example. How about f of x equals the square root of x? Here we have to recall that the square root of a negative number does not correspond to a real number. So in this case, the implied domain is all non-negative real numbers, or 0 to infinity, including 0. So whenever you're trying to determine the implied domain of a function, you're going to need to examine the expression and ask if it's ever undefined, or like in this case, if it doesn't represent a real number. Once we've established the domain of a function, we can evaluate the function at any input from that domain. We use the term evaluate to mean that we are putting in a chosen input and determining what the corresponding output is. For example, suppose f of x equals x squared. If we want to evaluate the function at, say, x equals 3, then that means we want to find what f of 3 is. And in this case, that means we're going to plug 3 into the function, work it out, and discover that f of 3 equals 9. It is important that we distinguish the term evaluate from the term solve. We solve when we are trying to determine when an equation is true. So we evaluate functions, but we solve equations. In terms of functions, this is the case when we know the output and wish to determine what the input or inputs are that produce the said output, if any. For example, suppose we start with the constant function, f of x is defined to be 5. If we are asked to solve the equation, when does f of x equal 5, then all real numbers are solutions. And if we are asked to solve when does f of x equal 1, then there are no solutions. So f of x equals 5 is true for all real numbers, while f of x equals 1 is true for no real numbers. When we work with more complicated functions and need to solve, this is where we need robust algebra skills. Of course, we'll be working on those skills all quarter, so before we worry about that, let's end this lecture by discussing an important prerequisite concept for calculus, namely the idea of net change in a function. In calculus, we are concerned with how continuous functions change over their domains. We'll talk about continuous versus non-continuous functions later. The point here is that net change plays an important role in later mathematics and also in applications. Despite its importance, the concept of net change is actually pretty simple. Given a function f, the net change in f from x equals a to x equals b is simply f of b minus f of a. In other words, it's just the difference in the outputs. If this quantity is positive, then there has been a net increase in the function. If it's negative, then there is a net decrease, and if it's zero, then there is no net change. An obvious application where this is important is in finance, where an investor might want to know what her net earnings are. If the net change is positive, she has made money. If negative, she has lost money. And if zero, then she is no better or worse off than she was before. In this lecture, we've reviewed the basics of what functions are, the notation we use, and some important preliminary terminology that you want to make sure to have a good grasp of. In the next lecture, we'll take a look at piecewise functions. See you there.